Hi everyone, my name is Devin Penny, and we're going to talk to you today about creating volumetric visual effects in Unreal Engine. I'm going to talk to you about Niagara Fluids, then my colleague Tim is going to go into detail about Sparse Volume Textures, and finally Patrick will finish up by discussing rendering with heterogeneous volumes. So this is a shot we created using Unreal Engine. The windmill fire was created with Niagara Fluids. It used a workflow that generated it fully in Engine to get really high resolution simulation results. The ground fire was imported from Houdini using SVTs, and everything was rendered together using heterogeneous volumes. It all used the same tools you'd expect in the engine, so lights, geometry, sequencer, MRQ, and all the other tools you'd expect to get sort of this type of shot done at a really high quality. So we're going to talk about all the different elements that went into this shot, including how we built, simulated, cached, and rendered all of the different volumetric elements. First, we're going to talk about Niagara Fluids. So Niagara Fluids is a tool set for creating 2D and 3D gas and liquid simulations for both real-time and cinematic use cases. So this could be a whole range of things. So for instance, for this year's GDC and the Electric Dreams demo, we did a full 3D liquid simulation in real time in that game environment. We also used it for that cinematic shot that was pre-rendered. You could also use 2D camera-facing gas and liquid simulations for games or maybe the ICVFX shots, that kind of thing. And it's all fully built in Niagara, using sort of the tools you'd expect from that. So we use reusable modules and pre-existing modules in Niagara. So as a power user, you can open up the simulation and change things. You can add behavior and remove things as you want pretty easily. And it's all modifiable using something called summary view that we'll talk about a little bit. But when you use Niagara Fluids, the big advantage is that you don't need to go to and from a third-party package. You can do everything in Engine. An important but very simple concept that will underpin most of the things we talk about in this talk today is the idea of data being stored on grids. So we're going to talk a lot about 3D simulation. We're going to show a slice, or you can imagine it's a 2D sim, doesn't matter. But here, you have grid cells and values stored in the grid for the simulation data. It could be velocity, or in this case, in that reddish color, we'll say it's temperature. And the higher the resolution the grid goes, the more detail you get, but it comes at a cost, both in terms of the computational performance and just the memory usage overall. So keep that in mind with a lot of the stuff we're talking about. So the focus of the talk today, for my part, will be the 3D gas solver. And so this is what we use for the windmill effect. You could use it for all kinds of volumetric gas effects other than fire and smoke. So, clouds and dust and fire, I don't know, sort of magical things. But, it's all sort of controlled using Niagara particles to emit fluid into the grid cells, and using geometry in your scene to collide against, and to sort of configure it using summary view. And keep in mind, one thing is that all of the solvers that I mentioned, 2D, 3D, gas, and liquid, they all use very similar simulation primitives and control mechanisms. So all of these concepts apply to all the different simulators. So for example, here we have some animated particles using Niagara. They have some color and radius and just some motion that's defined by some modules. And the goal here is we want to take these particles and inject them into a fluid. So when we sort of say, hey, what is this particle overlap, and what grid cells, and then just splat that color into there and let the fluid carry that around, this is something like you'd get. And also, we want to do collisions. So when you do collisions, for this case, we have this anvil asset, and it just falls through this sort of cloud of dust or something. And it's using the full 3D shape of that geometry because we take advantage of mesh distance fields. So it's something that if you have it available in your project already, then you can use it as a collision object in Niagara Fluids with no other computational cost. So an important thing to consider here is what actually gives the fluid motion. And a really important component to that is the pressure solver. And so the pressure solver is something that does a bunch of math in order to make sure that the velocity of your fluid is non-divergent. And you can imagine an easy way to visualize what this means is on the right, we have two examples of a pool of liquid. And the one on the right doesn't have enough pressure iterations to maintain the internal pressure so it keeps the same volume, where on the left we have enough and it's just a static pool until something actually drops in it or affects it. So in addition to sort of maintaining volume of liquids, it also applies to 3D gas simulations. It's the same solver. And so if you don't have enough iterations sort of on the left-hand side here, you'll get fluid motion that expands more than you'd expect and doesn't have the fluid like swirliness, vorticity. But then on the far right, let's say we give it a ton of iterations, like 1,000. It's a very slow simulation, but it converges to something, because if you look at the 150 iterations, there's really not a real appreciable difference between those. So some of it's an artistic thing, like you might want to choose pressure iterations to give you what you want, but also if you want to have it be convergent, it's something to consider that you don't need an egregious number of these to get what you expect. And so what we use to control all of this is a feature in Niagara called Summary View. So this is a place to sort of collect all of the parameters from all of your Niagara modules into one place that's very easy to access on the emitter inside of your Niagara system in the Niagara editor. And we have tabs and organization of all of the parameters that you'd expect to control a liquid simulation or a gas simulation. And all the things we talked about with sourcing and collisions, they all have parameters here to change things. And we also have a couple user parameters that you can kind of see in blue there. And those are things that are exposed to you on the asset itself when it's an actor in your scene, so you can just change things and connect it with blueprints or sequencer and stuff like that, so you can do some pretty complex effects. And one thing to keep in mind here is that this is not specific to Niagara Fluids. This is a tool that you can use in any of your Niagara systems, so I encourage everyone who's building things in Niagara to look at Summary View. And so what we're going to go through next is a little example of actually putting the asset from that windmill fire into a map. So the first thing we want to do is kind of size that box for your fluid, make sure that it encompasses the windmill blades, and move it in place, orient it with the blades. We're leaving a little bit of extra room on the left because we know that we're going to have some wind that affects the fluid. And the next thing we want to do is we want to make sure to add a source to it. So we have a user parameter set up on the right that is for some source geometry to emit from, so we connect the windmill blades. Obviously, this makes some really out of control fluid because there's no animation. So we go to sequencer, we're gonna add our simulation to sequencer, so we drag it in. We make sure to add that life cycle track that you need to do and set it to desired age. And after we do this, we're able to play and see something that roughly approximates what we had. It's at a lower resolution, so we're keeping it low because we want to be able to work really quickly and be able to iterate fast and just add all the features we want to the simulation. Okay, so the next thing we're going to do is we want to add some wind. So we open up the Niagara editor, and we're going to go over to that summary view we talked about and find the wind tab, the forces tab and wind. Check that on. And after we check that on, we already added some settings here that we like. So we're going to close it and go back to sequencer. And when we go to sequencer and play it, you're going to see that nice right to left motion of the fluid. And so, at this point, we're going to say, yeah, this looks pretty good. Like, I think we want to cache this out. And, so we can send it off to someone else to use or things like that. So what we're going to do is add that Niagara cache track on your sequence. And one thing really important to note here is that everything is done where we have overrides. So when we set it to cinematic scalability, it will run at a higher resolution. So we're going to cache it out at a higher resolution than we were running. And note in the future, that's going to be a much easier workflow than having to actually set it. It'll just be run when the cache is run. So now that we cached it, we can scrub around in the viewport or in the Niagara editor. Sorry, in sequencer. And you can play through to see it line up with the animation of the windmill blades. And gives a good approximation to what the actual final shot was. And we noticed something, oh shoot, we didn't put the timeline to where it should be. So we need to make some changes, and it looks like the windmill blades aren't really affecting the fluid. So let's go back and make some changes. So we'll drag that out to the end, make sure to mute that track. So we're gonna go back to the lower res live simulation. And again, something that will change in the future, we're gonna shift the scalability back to epic. And when we play, this is back at that live lower res sim. And we were looking at this and like, well, we could use a little more extra detail in the motion of the fluid, just from the blades of the windmill affecting the fluid. And we have this geometry as a sort of this hidden proxy geometry I already set up. And we want to make sure that that can actually be used as a collider for the fluid. And we have a system with just leveraging actor tags. So go into the tagging, select the actor tag, and make it a collider. And after we do that tagging, if we play now, we'll get a little more secondary motion from the blades interacting with the fluid and sort of dragging the smoke around. And that applies, that's sort of default with all fluids, is that you can do that tagging system in order to define your colliders. So we're gonna go back, we're gonna unmute the cache track, we're gonna make sure the scalability is set back to cinematic, and we are going to cache it once again. And this cache is at a higher resolution, like I said, so 16x, it takes a little bit of time to cache, but it's very manageable. And after we cache it, we can play. And we can see that extra motion we're getting now at a higher resolution with the collision objects, and also the full frame range, because we did that. And maybe you want to look at it through your cine camera to sort of get a view of what it would look like with that final shot that we showed originally, and sort of explore, like maybe what are the next round of changes that we want to do to this to sort of improve the look. And obviously you don't need to do that. Like one thing that we haven't talked about is the idea that you can just sort of get in really close to your simulation and inspect it. And this is one thing where using SVTs for caching is really helpful, is that you can freeze on a frame and go back and forth and kind of figure out like maybe there's something I need to debug or change in the next run of the simulation. And because all this is done in Engine, your next simulation is as easy as just pressing the red button to do the caching. Okay, so in conclusion, we're doing this shot, we're simulating in real time at 40 FPS in this example to sort of get the broad strokes of your simulation. We're doing higher resolution simulations for the caching, which is useful for lighting and integration work to pass off to other people. And then when we do the final simulation for the final render, we were simming at a velocity that has the resolution of that cache sim, but then making the density and temperature much higher resolution in order to get really, really fine detail. So next, Tim is going to talk about sparse volume textures. Go.
Hey everyone, my name is Tim, and well, let's talk about sparse volume textures. So now that we have a way of generating volumetric data, we need a way of storing it and sampling it at runtime. Regular 3D textures would be a simple solution for this. They are already supported, and pretty much all graphics APIs are exposed in Unreal and allow for fast runtime sampling. So, job done? Unfortunately, no. Since 3D textures densely store their data, their memory requirements grow cubically. This simply does not scale for the types of volumes that we want to use, so we need to come up with something else. VDB files are a popular solution for this in offline rendering. They can store volumetric data in a sparse way, utilizing a tree structure under the hood to only store relevant parts of the volume. Let's look at the pros and cons of integrating direct support for VDBs in Unreal. So on the upside, there are lots of existing assets and tools, so it will be easy for users to adapt this new feature in Unreal Engine. There's a library like OpenVDB and NanoVDB. They could be used to accelerate implementation. And the format itself is also very flexible, so artists could make very different uses of this, and this would see wide adoption. The downside being that the stored data is not natively filterable and needs to be manually converted to floating point values, which isn't that fast. And due to the tree structure, a single sample involves many buffer fetches, which also is not a point in favor of performance. And we will need to be able to stream animation frames into memory. By committing to VDB, we lock ourselves into that format, making streaming optimizations in the future harder to implement. Now, let's look at the third alternative, a custom solution for sparse volume data. On the upside, we get full control, so we can optimize everything to best suit our use case. We might even be able to make it fast enough for real-time applications like games, while at the same time scaling up to production assets. The downside being that, well, we need to implement everything ourselves, so this costs engineering time and maintenance down the road. As you can tell by the title of the talk, in the end, we decided on investing the time to implement a custom solution. But that is not to say that we ignore VDB. Unreal Engine can import VDB files and converts them into our own custom data structure, so there's no need to reauthor all your volumetric assets. So let's get right into it. Our custom solution, Sparse Volume Textures, or SVT, works like this. First, we split our volume into small cubes, which we refer to as pages. Pages containing actual voxel data are packed into a 3D texture, while empty pages are ignored. That texture is called tile data texture, because it stores the actual voxel data. I'll get into the distinction between tile and page in a moment. In the lower left corner, you can see a slice of the 3D tile data texture of our Fire asset. We have another 3D texture with 1 voxel per page. That texture spans the entire volume, and each entry points to a tile in the tile data texture, or has a null pointer if that page is empty. We call this the page table texture. We have an optimization where pages with identical voxel data share the same memory in the tile data texture. So you can think of pages as a logical chunk of the volume, while a tile is the actual data backing one or multiple pages. Now, if we want to sample the SVT, we first need to compute the coordinate of the relevant page, sample the corresponding pointer in the page table texture, and then use that pointer to sample the tile data texture at the correct location. Thanks to this indirection, we only need to spend memory on parts of the volume that have actual data in it, which saves lots of memory on sparse data sets. As you can see in the bottom right image, only the colored cubes have voxel data in the tile data texture. All the empty space in the bounding box around that Fire doesn't take up any memory in the tile data texture. Of course, sampling the SVT is now a bit more expensive than sampling regular 3D texture because we need to sample 2 textures, but it is still faster than going through a multi-level tree structure implemented as buffers. And that's the important other point. Our data is stored in textures, so we get native GPU support for different texture formats and can do fast filtered sampling. Currently, SVTs can be created from Niagara Fluids and by importing VDB files. In this section, I'm going to focus on the latter. Volumetric data often has more than 4 attributes or data channels. In order to support this, we actually have up to 2 tile data textures per SVT, sharing a single page table texture. The pixel format and number of tile data textures depend on the import settings, so it is important to pay attention to this step. In the import options, you can see 2 sets of attributes, attributes A and B. Each set of attributes corresponds to 1 tile data texture. The import dialog essentially allows you to map grids from the import VDB file to texture channels of the tile data textures of the resulting SVT. Unfortunately, we are limited to 2 gigabytes per tile data texture, so for large assets, it is important to try to reduce the memory footprint to fit the data into that limit. This is mostly a concern for non-real-time use cases, but keeping the memory footprint as low as possible is also important for real-time to keep the burden on a streaming system as low as possible. I'll get into that later. What's important at this stage is to make sure you use the smallest possible format for your data. While we do support 32-bit float, it's often better to use 16-bit float instead. For density, you could even get away with using 8-bit UNOM. Since we have linear filtering, you shouldn't see any stepping artifacts between neighboring voxels. And also, please only import the data you actually need. In the 2 images on the right, you can see what optimized import settings would look like for my example assets. I switched the first texture from 16-bit to 8-bit and removed the unused channels. Also note how the importer automatically detects that it is dealing with a sequence of VDB files. You can untick the checkbox if you only want to import that single frame. Now, onto material integration. SVT are fully integrated with our material workflow, so you can sample them in any material graph, just like any other texture. In this image, you can see the simplest reasonable way of sampling a SVT that I could come up with. We compute 3D UV coordinates by remapping the local position in relation to the bounding box and then plugging that into the sparse volume texture sample node. We store density in the red channel of attributes A, so we mask that out and plug it into our extinction. Since SVT acts like a regular texture, you can use it however you like, so it doesn't even need to be a volume domain material. However, SVT are probably most useful if used with volumetric fog, volumetric clouds, or heterogeneous volumes. These techniques require the material to be a volume domain material with additive blend mode. Also note that for animated SVT to work, you will need to use a SVT parameter node. I'll explain why that is in a moment. But let's take a look at MIP levels first. SVTs are fully MIPed. This is necessary for streaming, but the MIPs are also exposed to the material, so you can explicitly sample at different MIP levels. The SVT sample node automatically loops between MIPs if you supply a fractional MIP index. In the future, we might also leverage this to offer lower resolution versions of the same volume on weaker machines, so it would effectively become a scalability option. All right, now let's get back to a more interesting topic. SVT supports animations. VDB represents animation as a sequence of files, but in UE we have animated sparse volume textures, which is a single asset holding all the animation frames. Each frame is in itself a SVT. Playback essentially works like a flipbook animation by swapping out the currently displayed frame. In order to do this, we first need to extract the individual frames from the SVT, then bind them to a SVT parameter node in our MID of our material. Sorry, our material instance dynamic of our material. There are multiple ways to do this. You can use Blueprint, C++, or the Heterogeneous Volume component. I recommend the latter because it does all the heavy lifting for you, but using Blueprint or C++, you can use animated SVT for different effects like volumetric fog or clouds. Our online documentation on SVT should have a section on how to set this up with blueprints. Now, let's talk about streaming. Streaming is absolutely necessary to deal with the limited memory we have on the GPU. In addition, there are also allocation size limits imposed on us by the graphics API. So unless we have fairly small volumes and short sequences, we can't keep all the data in memory at the same time. Voxel data is streamed into pre-allocated tile data textures. So at any time, there are likely multiple frames of a given SVT sharing the same tile data texture. We currently stream at MIP level granularity. The streaming system detects the direction of playback and automatically prefetches MIPs of upcoming frames. Whenever data hasn't been streamed in yet, the renderer falls back to using coarser MIP levels. While developing SVT, we noticed that even within a single page, there's often considerable sparseness. So we introduced a compression scheme to get even more compression for the streamed-in data itself. We've seen 30 to 50% savings in the data that we need to stream in with this compression technique. It's based on using occupancy bit masks. What I just described is mostly relevant for real-time applications. If you're using the movie render queue, you're probably interested in always having a certain SVT frame fully streamed in before you start rendering. This is supported in the form of blocking requests. When you're using blocking requests, the streaming system will immediately wait for each requested frame to be fully loaded in. This is a trade-off between frame time and quality. So as you can imagine, waiting for hundreds of megabytes or even a few gigabytes to finish loading in the middle of your frame is going to have an impact on your frame rate. Now we're coming to what I think is the most important slide in this section of the talk. Performance and memory tips. For SVT, performance is directly related to memory, so you will want to optimize your memory footprint. Even if you're not using SVT in a real-time setting, bigger SVTs take longer to process during import and to load in, so optimizing your asset might save you some time down the road. Like I said before, the streaming system will fall back to coarser MIPs if it can't catch up. We call this dropped MIPs. Note that this only applies to non-blocking streaming. See the video on the right for dropped MIP levels in action. In order to prevent this from happening, we need to ensure that the streaming system isn't overloaded. If possible, try to reduce your memory footprint by using smaller formats during import and by importing fewer attributes. You can also use fewer frames and a lower frame rate to give the streaming system some time to stream in each frame. You could try to hide that lower animation frame rate by lerping between SVT frames in your material. Obviously, you could also just use a lower resolution input volume. Another neat trick is to crush small values to 0 in your DCC tool of choice. We've noticed that there are often very small but still non-zero density values in volumetric assets. Although these small densities contribute pretty much nothing to the final look, they still take up memory. In a way, the threshold below which you crush the values can be used as a scalability setting. And finally, you can make the interior of your volumes homogeneous. SVT recognizes chunks with identical voxel data and only stores a single tile worth of voxels to represent the entire homogeneous region. I realize that this might be some effort when authoring the volume, But we've seen a certain famous cloud asset make use of this, and it saves quite a bit of memory. I would also like to point out that SVT was just released and is still experimental, so streaming performance is likely to improve in the future. And now let's see how we imported and set up a SVT asset in our shot. First, we drag one file of our VDB sequence into the content browser. In our setup, we only care about density and flame and put both of them into attributes A. For attributes B, we can just set all these entries to none and then click import. Next up, we'll need a material to use our new asset. In this material instance, we already have a bunch of rendering parameters ready to go, so we'll just override the SVT parameter to point to our asset. Now, we need an actor in order to render it in our map. So we create a basic actor and rename it to something sensible. Then we add a heterogeneous volume component to that actor and set it to use the material we just set up. You can now see the very first frame in our SVT. In order to actually see it play back, you can set it to playing and looping. Note how we are dropping MIPS. This is a cinematic shot, so we don't really care about real-time streaming performance, so we can just set it to use blocking requests, which eliminates the issue. Next up, we're going to place it in our shot. Now that we have it in here, we want to activate it from the sequencer, so it lines up with our fire simulation. To do this, we drag in our actor, add the heterogeneous volume component, and then set the frame property. We have a run-up to our fire simulation, so we only start the SVT fire at frame 101 in sequencer and end at frame 400. We also need to make sure we're using linear interpolation. Now that we have everything set up in sequencer, we can see both effects when scrubbing live through the timeline. If we want to play it, you'll first see the run-up for the fluid simulation, and eventually the SVT fire will kick in. For our shot, we only care about frames after that run-up section. And of course, you can also go in, zoom in, and take a different look at things. All right, so in conclusion, we now have a new asset type to deal with volumetric data. Depending on your assets, it is even usable in real-time applications. We are working on improving that one. It is fully integrated within our material graph workflows and supports animation sequences. You can create SVT assets by importing VDB files, but it is also used by Niagara Fluids for caching simulations. And now Patrick is going to dive into how heterogeneous volumes can be used to render our volumetric assets.
Hi, I'm Patrick. I'll be discussing the rendering of Niagara Fluids, SVTs, and SVTs with our heterogeneous volume rendering system. First, to give some background, heterogeneous volumes was first released in 5.1. Its initial goal was to replace the bespoke rendering technique that originally shipped in 5.0. The original system had supported a limited lighting setup and required use of custom HLSL compute nodes in Niagara, so it limited its interoperability with the rest of the scene. In contrast, heterogeneous volumes was developed to be more integral to the set of render passes, which inherit existing scene lights and other native UE constructs like the depth buffer and shadow maps. Exposing shared internal structures from the heterogeneous volumes passes will also make future integration possible, such as rendering with translucency, for instance. Another design goal for heterogeneous volumes is to create a quality scaling option that's beyond that of UE's volumetric fog. Niagara Fluids can create voxel volumes that are close to pixel level resolution, while volumetric fog prefers to operate at a lower resolution and generates a lower looking frequency volume as a result. Volumetric fog also doesn't support self-shadowing, which is essential for the look of these high quality volumes. One of the later design goals was to add support for sparse volume data formats, but this is actually orthogonal to the implementation. By abstracting the volume data at the material evaluation level, heterogeneous volumes can remain agnostic to the volume input format, so it can be dense, sparse, or even procedural. Due to the demands of the pixel level quality with accurate self-shadowing, we decided that heterogeneous volumes should initially target cinematic and virtual production use cases. We also added path tracing support for heterogeneous volumes to complete the scalability path all the way through offline rendering. However, it wasn't immediately clear if we could use this as a fast real-time method. At the same time, UE already has volumetric fog, which is a proven performance technique. So what we decided to do was provide a natural degradation path from offline heterogeneous volumes to real-time volumetric fog. And again, we're leaning on the material graph to provide this abstraction. So basically, elements that are authored in heterogeneous volumes can also emit as volumetric fog elements for platforms where it isn't supported or where it's disabled. When it comes to maintaining and maximizing a runtime performance, it's important to keep several properties in mind when using heterogeneous volumes. Virtually all the runtime costs associated with rendering heterogeneous volumes are proportional to the voxel density of the volume and the number of lights illuminating the volume. So lowering the number of voxels and the number of active lights will have a measurable impact on performance. So it's very important to keep these in mind and model efficiently. We expose several primary controls on the heterogeneous volumes component and the Niagara volume renderer properties to aid to control both performance and quality. The most impactful scaling property is the lighting downsample factor. Together with the native voxel density of the volume, the lighting downsample factor controls the density of an intermediary lighting cache, which is responsible for storing in scattered radiance at the voxel volume. This accelerates the lighting computation. So the lighting cache decouples expensive shadow queries that would ordinarily be used or be calculated in the primary ray marching loop, and this prevents us from having to repeatedly ray march for each contributing light. If the lighting downsample factor is set to 1, then the lighting cache has the same voxel resolution of the native volume being rendered. And if it's increased, then it will shrink the dimension of the lighting cache by this factor. It has a staggering impact on performance, but it's going to also decrease the quality. We found that rendering with a lighting downsample factor of 2 is a good starting point to maintain performance without sacrificing too much quality. But when rendering play blasts, like in our example here, it's recommended to change this value to 1. The next 2 parameters have very similar applications, but they're decoupled for semantic customization. So the step factor and the shadow step factor control the ray marching step sizes in voxel space. And when both factors are set to 1, you're again ray marching at the native voxel resolution of the volume. And when they're increased, the step sizes are now increased proportional to what that native voxel size is. By default, we ray march at a step size of 1 and a shadow step size of 8. And this is the right sort of performance quality threshold that we've shown, that we've seen doesn't show much quality loss. Again, if for the purposes of rendering cinematic, we recommend that you would just set both of those to 1. Both Devin and Tim have already shown you sort of basic setup for Niagara Fluids and heterogeneous volumes, so I'm going to dive in a little bit and talk about more of the rendering details at play that you might encounter when you're rendering heterogeneous volumes. So let's first take a look at our shot and freeze simulation. And for this breakdown, I'll be focusing on the ground fire. We'll move a little bit closer. So if I uncheck the cast volumetric shadow option from the directional light, it'll highlight the importance of self-shadowing. Without self-shadowing, our renderer starts to look similar to that of the existing volumetric fog solution. And you can probably already see some shadowing artifacts here as the idle tree animation is casting through the volume. The artifact is coming from the undersampled lighting cache that I was just referring to. And as I discussed earlier, the default value of the lighting downsample factor is 2, creating a lighting cache that's approximately at half resolution in each dimension. In case the artifacts aren't clear, I'm animating the downsample factor here to oscillate between 1 and 4. We really start to take a noticeable performance hit as we start shrinking the lighting downsample factor, because now we're operating closer at the native voxel resolution. And if you look very closely, you can still see some artifacts just because the actual voxel resolution is slightly higher than pixel resolution. But I'll move in a little bit closer to demonstrate that because it may not show well on the projector. So we can actually achieve pixel level lighting by modifying the interpretation of that lighting cache. Instead of storing in-scattered radiance, we would be storing transmittance. This allows us to evaluate pixel level lighting through the main loop where we'll only query transmittance instead. I really wouldn't recommend this for anything other than pre-rendered cinematics because it's quite taxing. It involves a number of compositing passes that increases linearly per light. But we'll put this in the forthcoming documentation so you can run it if you need to. I'm going to go ahead and move back a little bit and focus on the original view. So under motion, the artifacts are pretty hard to detect. With self-shadowing added back in, the artifact is almost imperceptible. And for this reason, we're using the standard lighting cache with the standard lighting downsample factor of 1 for our cinematic. Go ahead and drop the sun and move to a different view. And I'm also going to trim a little bit of the scene just to isolate some of the problems. Or some of the features. So far, we've primarily seen heterogeneous volumes lit by the natural sun and sky models, but we can also use local lighting. And here I'm showing a point light acting as key and an off-screen rect light as well, lighting the volume. And here's a turntable using 3 different spotlights under some animation. As I mentioned earlier, we can also use the path tracer to render heterogeneous volumes. Heterogeneous volumes integrate within the same existing framework that makes height fog and reference sky atmosphere possible. The framework was extended during this period to support volume emission. And by presenting a unified model for light transport, the path tracer can accurately and easily account for contributions that are not easily expressible right now in the deferred rendering solution. So in this example in particular, you can see the complicated volume casting shadows that are animating on the ground. That's not possible today in the deferred renderer. And in this example, you can also see some of the multi-scattering effects like the fire emission illuminating the smoke. It also creates a very subtle glow and adds reflected flame that you can see shining off the rocks in the foreground. In comparison to the full multi-scattering solution of the path tracer, the deferred rendering path needs some more development before we can correctly integrate with all of the existing render passes. The features here that I've listed are the highest priority for active development, and know that they're receiving attention now as we're transitioning beyond the 5.3 release. Finally, we're excited to start pursuing real-time applications on PC and even potential applications to modern console hardware in the near future. All right, now it's time to wrap up our talk. So we've demonstrated 2 methods for creating and rendering volumetric visual effects with Unreal Engine. With Niagara Fluids, we can create an entirely closed-loop solution within our ecosystem. And with the Sparse Volume Textures, we can import external data sets as well. Both volume types can be rendered at high fidelity with the new Heterogeneous Volume system. The addition of Niagara Fluids, Sparse Volume Textures, and Heterogeneous Volumes brings some additional cinematic realism to existing environments. It wasn't possible before. We're excited to see what you'll create with it. And I wanted to remind you that everything you've seen here is available now. Our cinematic in particular was built on top of the 5.3.1 release. So there's no hidden features here. It's all available for you. And stay tuned for future improvements because more are coming. We also wanted to take a moment to thank some folks. We wanted to thank Dan Pearson and Wyeth Johnson for their contributions to our presentation, and Sebastian Hilaire for the initial design and development towards the implementation of Sparse Volume Textures. And lastly, we also want to thank the countless artists and engineers at Epic for giving us motivation and support.